Hello, I'm Weihan, a PhD student hopefully graduating next year. And I'm happy here to talk about our work, fast-read Solomon IOP multivariate polynomial commitments and verifiable secret sharing. This is a joint work with Professor Zongyang Zhang, my group mates Yanpei Kexin at Beihang University, my host Professor Sherman Chow at CUHK, and Ximeng from Fuzhou University and Jin from Beijing Academy of Blockchain and Edge Computing. And a polynomial commitment involves two parties, a prover and a verifier. The prover wants to convince the verifier the validity of some public evaluations on a committed polynomial. Typically, there are three sub-protocols. The generation protocol generates public parameters, BP. The commitment protocol takes the polynomial as input and outputs the commitment. And given an evaluation point Z and a claimed evaluation FZ, the prover and verifier invoke the evaluation protocol to prove the validity. And the evaluation protocol can be a public co-interactive argument knowledge and can be made non-interactive via the standard field Shamir transformation. And recent years have seen many polynomial commitments from different groups, and we focus on fast-read Solomon IOP, or FRI in short, which avoids group arithmetic or assumptions. Instead, it relies only on lightweight field operations which are concretely efficient. They also offers transparency and practical benefits such as polylog, verified complexity, and proof size, about several hundred kilobytes in practice. State-of-the-art FRI-based polynomial commitments achieve optimal quasi-linear commitment complexity due to the read-Solomon encoding. They also maintain polylog verified complexity and proof size. However, while univariate FRI-based polynomial commitments can reach the optimal linear prover complexity, multilinear polynomial commitments are limited to the quasi-linear prover. So our first question is, can we build a FRI-based multilinear polynomial commitment with a linear prover complexity? And next, we ask, can we achieve a one-to-many polynomial commitment? So a one-to-many polynomial commitment considers one prover and n verifiers. The input is a size n polynomial fx and its commitment c. In the one-to-many evaluation proof, the prover generates n proofs, each proving the ith evaluation to the ith verifier. Instead of requiring n times the underlying proving time, which is at least n squared, a non-trivial prover complexity for univariate polynomials is n log n. This is optimal for being the same as using FFT to compute polynomial evaluations. Previous work showed that the one-to-many polynomial commitment has applications to verifiable secret sharing, or VSS. And in a VSS, a single prover wants to securely share a secret to n verifiers. To do this, the prover splits the secret into n pieces, sending the ith piece to the ith verifier. If enough verifiers get together, they can recover the secret. And any subset of verifiers smaller than t can learn nothing about the secret. We generally assume that t is on the same order as n. So we can build a VSS from one-to-many polynomial commitment. It's a Shamir VSS, and the prover's secret is a constant term of some size t univariate polynomial. She sends a distinct evaluation and its corresponding polynomial commitment proof to each verifier. And each verifier checks the validity via the polynomial proof, and the verifiers can recover the secret S by polynomial interpolation. So it's clear that using the one-to-many polynomial commitment, the prover can generate n proofs more efficiently. VSS can be synchronous or asynchronous. Asynchronous VSS or AVSS doesn't assume a bounded network delay, which reflects the real-world constraint better. So in an AVSS, an honest verifier might not receive the prover's message in time, leaving others uncertain whether the delay is due to network issues or if the verifier is just malicious. Such uncertainties can make secret recovery field. So our AVSS uses bivariate polynomial commitments and a technique of share of shares to handle the possible delay. Now, the secret is the constant term of a t-degree bivariate polynomial fxy. The prover sends fi1 to fin and proves pi i1 to pi in to the ith verifier. To handle the delay of the second verifier, for example, the ith verifier sends fi2 and pi i2 to the second verifier, allowing him to recover fx2. If the ith verifier has fxi, then t verifiers can recover fx0 and hence the secret f0, 0. So with this still a core procedure, and we observe that the two verifiers can be seen as a combined single verifier. Now the question becomes, given a bivariate polynomial fxy, how can the prover prove the validity of evaluation Fij to the combined verifier representing both the ith and the jth verifiers? And this is exactly a one-to-many polynomial commitment for n-square evaluations and bivariate polynomials. So can we achieve a one-to-many bivariate polynomial commitment? And note that we need a different approach from existing works, which can be challenging to be generalized to bivariate. Finally, can we improve AVSS using our polynomial commitment? As expected, the answers are all yes. So we improve the polynomial commitment in HyperPlonk and achieve to reduce the prover complexity to optimal linear. Second, we build such a one-to-many polynomial commitment, and for n-square parties, the prover complexity is n-square log n, which is still optimal for being the same as running FFTs for bivariate polynomial evaluations. Finally, we construct a new AVSS scheme with a linear complexity of n-square log n, which follows existing works basically using polynomial commitments. And next, we'll dive into some technical details of the first two contributions. So let's first recall why HyperPlonk polynomial commitment requires a quasi-linear prover complexity. So in the evaluation protocol, the prover needs to generate and commit to log n new polynomials, where the ith polynomial has a size of n times 2 to the power of negative I. The prover then opens several evaluations on all these polynomials and uses a univariate batch fry to open them efficiently. However, the batch fry requires all polynomials of the same size. So the prover must pad all log n polynomials into the same size of n and commit them using the Merkle tree, which already costs quasi-linear time for proving. So to solve the problem, we observe that the polynomial size reduction naturally occurs within the evaluation protocol of each polynomial independently. For example, to open some evaluation on f superscript 1, Fry reduces it to a smaller polynomial f sub 1 superscript 1 of size n over 2. The polynomial has exactly the same size as f superscript 2, and we can combine these two polynomials without padding. And we can apply this combination recursively, such as combining half of f superscript 0 and f superscript 1 to obtain g1, and combining half of g1 with f superscript 2 to form g2. We call this approach rolling batch fry. And now we achieve a linear prover complexity without padding. Next, we overview how to construct a one-to-many bivariate polynomial commitment. We first propose an approach to transforming a bivariate polynomial into a multilinear polynomial of the same size. We then observe that our polynomial commitment, inheriting from HyperPlonk, handles variables sequentially one by one. This allows us a straightforward tree approach, and this slide shows fxy with a variate degree of 2 as an example, which takes 12 steps and the prover complexity is n cubed times log n. So we achieve a non-trivial one-to-many bivariate polynomial commitment by reusing the steps as much as possible. We first reverse the variable arrangement to place the high degree variables on the left, and this is equivalent to the original variable arrangement. And our next key observation is that in the VSS, the evaluation points don't need to be random and can be fixed in advance. So we then choose xi and yj to be roots of unity of 2. As the squares of any xi or yj are the same, we can reuse some steps as marked in red on the slide. And now we only need 9 steps, and the prover complexity is n squared log n. So we solve our research problems and propose a new Frey-based polynomial commitment, the one-to-many evaluation using this polynomial commitment, and AVSS using the one-to-many polynomial commitment. They achieve better complexities and functionalities. And we implemented our polynomial commitment and one-to-many polynomial commitment schemes named polyframe. Experiments show that polyframe achieves at least 5 times faster prover time than previous works, while the verified time and proof size are at least competitive. So in summary, we construct a transparent Frey-based multilinear polynomial commitment with optimal prover complexity, and we generalize it to one-to-many bivariate polynomial commitment, maintaining the optimal prover complexity. Finally, we construct an VSS scheme with n squared log n dealer time and a better trade-off. And thank you for your attention. I'm happy to take any question.